Okay, let's get started. So basically, I uploaded almost all the videos. So I'm trying to upload the latest one last time, but the network here is too slow. So I'll upload that tonight at home. So yeah, you should be able to see all the videos of this class if you missed any. Okay. All right. So any questions in general? Okay, if not, let's briefly go over what we covered last time. So basically, we talk about AM demodulation, right? And so we first finished the computation of power efficiency, and then we talk one approach for AM demodulation, so which is a square demodulation, right? So yeah, let's recall this is the definition of the power efficiency. So basically, it means the useful power divided by the total power and times 100%, right? And in order to compute the power efficiency, so we need to compute the total power and the useful power, right? And so in our class, we assume that the DC component of the message signal is 0, right? So that can make our life a little bit easier. And then we can compute the AM signal, the power of the AM signal, right? Remember that when we say AM, not power, not amplitude modulation. So basically, we mean this kind of signal, right? So we have a message part, and then we have the carrier part, right? So we need to transmit the carrier in this case. And in order to compute that, we break it into 3 parts, right? And the first part is relatively easy, right? So that's A/2. And the second part and third part is harder. So yeah, we focus on the computation of this part, right? So for the second part, so basically this is what we got, right? And if we do the direct computation, so we can get this formula, right? We have a cosine square here, right? We can use the trig inequality, trig identity to break it into 1 plus cosine 2 omega ct entire thing divided by 2, right? So this is what we got. And the first part may be OK to compute, right? Because we know the DC component is 0. But the second part may be a little bit troublesome, right? So it is not obvious what's the value of it. You can take a guess, but it's not obvious. So in general, in this class, so if we have some difficulty to compute something in the time domain, then we may want to try it again in the frequency domain to see whether it is easier or not, right? So we try that to compute it in the frequency domain, and so this is what we get. So first of all, remember, so from here to here, so this is Parseval's relationship or Parseval's theorem, right? So yeah, when these two signals are identical, so that will become the power, right? All right, so the Fourier transform of this guy is this, and the Fourier transform of this guy is that, right? So that is relatively straightforward. And then we need to compute the inner product between this and that, right? So then we have 4 terms here, right? Plus minus means that we have all of them, right? Okay, and then, so from here we can get this, right? We have 4 terms here, and then if we write it out, we have these 4 items here, right? Clearly, the middle items are the DC component, and then we got this and that, right? And we claim that this is 0 and this is also 0, right? I think in class, so I made a mistake. So basically, in the class, when I was trying to explain that, so I drew 2 figures. So this is M of F, and this is the shifted. Oh, let me write it more clear. So this is a shifted version of it, FC, and here is minus FC, right? So what we care about here is this guy, right? M2FC. Right? I think in the class, I focus on this guy, right? Even for this guy, we evaluate this guy at M12C. I think it's still 0 because we have FC bigger than B, right? So yeah, but let's focus on this guy. So basically, we have 0 here, we have B here. Yeah, simply because FC is bigger than B, right? Then anything bigger than B would give you 0. Clearly, 2FC is bigger than B, so therefore, this guy will be equal to 0. Right? I think that is the correct explanation, right? In the class, I got confused, and then I focused on this guy somehow, right? Although for this guy, so at 2 times FC, so it will be still 0, right? So, okay, so is that clear for this one? So in the video, I mark it, so I made a mistake there, so I give a captain there. You can take a look, right? Be careful there, so it's easy to make mistake. All right, and so then the conclusion is that this inner product is 0, right? Which is very nice. Okay, and then we say, okay, so basically, if the inner product between this and that is 0, then we can say, okay, those two are what? Orthogonal to each other, right? Okay, yeah, and then we can compute the last term, right? So in order to compute the last term, the idea is the same. So we break this norm by this 3 component, right? And then we say, okay, this is 0 because so this and that, there's no any overlap, right? That's 0. And so the value of this and that, they're the same, right? It's just a shifted version of Fm, so the norm will not be changed, or the power will not be changed, right? So that will be the power, right? Because this and that are identical, and then so we can write the power of m of t, right? Okay, and if we denote the power of m of t as Pm, and then we know the carrier power is this guy, so this is the total power, right? And then we use the signal power divided by total power, so we get the power efficiency, right? So this is how we compute it, right? So if I have exact AM signal, you can use this formula directly without recompute it. Okay. Okay, very good. And then we'll give an example of the tone modulation, and from the example we can see that the best power efficiency for the tone modulation is 1/3, right? 33.3%, right? Which is very bad, right? Then we raise a question. Okay, so if that is bad, then why we want to use this? Why we don't use AM, right? Because the power efficiency is so bad, right? Most of the power will be used to compute to transmit the carrier, right? But we claim that okay, although the power efficiency is bad, but the demodulation is much easier to do, okay? And that's the reason we use it. And for the demodulation, so we introduced the square demodulator, right? So basically, for square demodulator, what we do is nothing but we just do a square of the received signal. Remember, so this guy is a received signal. Right now, we assume there's no noise, right? So the received signal will be equal to the transmitted signal, okay? And if we do a square of it, and then we can do some manipulation. So have a cosine square here, and then we do the same thing as before, so we get this kind of thing, right? And clearly from here, which is very good, right? We can use a low-pass filter to filter out this guy and remove the higher frequency component, right? But the loss here is that, so now, because we have the signal is squared, so the bandwidth will be doubled, right? So we need a wider bandwidth LPF. Or, if we transmit that in a realistic channel, we need the channel bandwidth to be bigger, right? So that's the downside of this, this demodulator, okay? So that is basically what we covered in the last time, right? Any questions? Okay, so today we're going to finish talking about AM demodulator. Today is our lecture 15. And first, we're going to talk about the AM demodulation. Okay, we're going to introduce you one more demodulator, right? That may not require the double bandwidth. And the second thing after this, so we're going to talk about the bandwidth efficient amplitude modulation. Okay, so yeah, we may not be able to finish all of them today, but here, give you a heads up. So basically, we're going to focus on 3 kinds of modulation here, right? As we said, right, the idea is that, so if we transmit a real signal, right, only half of the bandwidth, so if we move it to the passband, only half of the bandwidth carry information. So the other half is symmetric, right? So it basically means that we don't need to transmit the other half, right? How can we do that in practice? So mathematically, it may not be, it's pretty obvious to, but for in practice, let's see how we can do that, right? So the first is that we're trying to do exactly that, right? So this is called single sideband. So in contrast to the double sideband, right, DSB, right? So here we'll talk about SSB, single sideband modulation. Right, that's called SSB. And then we're going to say, okay, so in the single side, as in the SSB, so it may not be easy to do in practice, right? Because it requires some higher order filter, right? And then let's relax it a little bit. So basically, that is called vestigial sideband modulation, or we call that VSB. Okay, who heard of this before? VSB? Only you? Who heard of SSB? You again? Okay. Do you know what VSB exactly? No. Oh, great. Yeah. Very nice. Okay, and then we say, okay, there's some downside of this too. There's some downside of this too as well. In order to solve the problem, so we're going to introduce you the most popular modulation that we're using today in practice, right? That's called, do you know what that's called? Yeah, that's called, I'm sure you heard of it. It's called QAM. Heard of it? Yeah. Quadrature yeah. And we use that for both digital and analog communication. Okay. Yeah, let's see. Yeah, normally I don't spell that. Quadrature amplitude modulation, or call that QAM, right? That can almost solve all the problems. Okay, and these are our agenda. So probably today we're going to focus on SSB. Okay. All right, so yeah, let's get started for the first part. Okay, so for the AM demodulation, the second one, so we describe that as rectifier or diode and envelope demodulation. Right here, we're going to come back to our original idea, of making sure that the modulation index is less than 1, right? Remember, so if the modulation index is less than 1, so the signal envelope will be above the 0, right? Then if we can detect the envelope, then we say it's good, right? Today we're going to see how we can do that exactly. So basically what I meant is like this. So if the modulation index is less than 1, so basically, so this is what we're going to have. Let's say here is our MT, right? And then, so for our AM signal, so that will be like this. Okay, yeah, this is our AM signal. Now we're going to see how we can demodulate that. Okay, so there are a few steps. The first step is called rectifier. Okay, what does this word mean? Rectifier. Yeah, actually, I don't know what this word means. So basically, I think it has something to do with rectangle, right? So basically, it means that we're going to get rid of half of the signal. Okay, so or we call it diode, right? Diode basically means that only one direction can go, right? The negative direction is blocked, right? So basically, the first step is that we're just going to retain the positive side of the signal and get rid of this part. Okay, so basically, yeah, this is the first step. Let's see, the first step is, yeah, we do the rectifier. So basically, after this, so this is what we're going to get. Okay, it's something like this. Okay, so this is the first step. And how can we do that? Yes, to use this, right? Diode. Okay, so pass the signal through a diode, and then, so this is what we can get. Okay, so basically, the circuit would look like this. We have a diode here, then a resistance. Yeah, this is what we get. So basically, our SAM input to this and passing through that. And now we have a signal after the diode. We have signal denoted as RT, right? And that is output signal. And so basically, that is this signal. Okay, and for this circuit, we call that half wave rectifier. Okay, great. So now let's see how we can do that mathematically, right? So this is what is happening. So basically, equivalently, RT equals to nothing but as follows, right? So this is our AM signal, right? So basically, what we do here is that we use this signal multiply a square waveform, right? But only on the positive side, right? In other words, so basically, we multiply this guy by something like this, right? And right, yeah. So yeah, my drawing is not that great. So basically, something like this. You get the point, right? So basically, just maintain this part, right? This multiply this kind of square chain. Okay. So in other words, so basically, let's say if our original, so yeah, so then yeah, we denote this square wave chain as WT, right? So basically, we use this guy multiply WT, right? So cosine multiply this guy is nothing but something like this, right? So basically, this is our cosine, right? So this is our cosine omega CT, and so for this square chain, so basically we pick the period of that is the same as the cosine, right? Something like that, and so on. Right, so this is what we do. Okay, yeah, this is what happened mathematically, right? In practice, it doesn't mean we use this multiply the square waveform, right? In practice, so this is what we do. Just pass that through a diode. Okay, but here is it's easier for us to analyze and help us to design the decoding approach, the demodulation approach. Okay, great. And from here, so how can we see how we can do the demodulation, right? So basically, the idea here, so the idea we use all the time is that we're going to pass this guy via some kind of low-pass filter, right? So it basically means that we need to get rid of the higher frequency component, right? And from this formula, can you tell me what would be the left after the low-pass filter, right? It basically means that we need to analyze, so what are the low-frequency component and what are the high-frequency component, right? For the first guy, so it's very clear, right? So we know the frequency of MT is MF, and we know cosine omega CT, it only has one frequency component, right? And how about this guy? So do we know the frequency component of this guy, this square chain? Do we know that?
We know that it's pretty high, right?
Yeah, we know that exactly, right? We did that in our lab 2 or lab 1. Lab 1, right? Is that lab 1 or lab 2? Lab 1. Right, we know that exactly. And so we also give you an example in class about this, right? We didn't compute that exactly, but we give you the slice of it, right? So if you forget, so you may take a look at the example 2.8 in the book, right? So it gives you the Fourier series of it, right? So yeah, the 5th edition, okay. Okay, so basically here, let me write it down. So basically, we can do the Fourier series decomposition of it, right? So omega t would be nothing but this. Well, 1/2 plus 2/pi. Then we have cosine omega t plus minus 3 omega t and 5 cosine 5 omega ct and so on. Right, so this is what we get. We only have the odd frequency component and we don't have the even frequency component. Do you remember? So we have a question on that, right? Okay, great. So this is what we do. Okay, so now basically, let's see what we're going to have. We use this guy, multiply that. So can we imagine what would be left? Right, so first of all, yeah, let's see whether you can observe it or not, right? So there are something that we really like, right? So we have a cosine omega ct here, and we have another cosine omega ct here, right? So this multiply that will give us what? A cosine square, right? So which we should like, right? Because we know how to deal with the cosine square, right? Okay, and so the first part, multiply the constant, will still at the frequency of omega c, right? So that is basically the higher frequency component, right? And if we use this part, multiply the rest of it, it's all high frequency component, right? So therefore, it basically means that the only low frequency component that we're going to have is using this cosine, multiply that. So everything else will be the high frequency component. Yeah, do you agree? Yeah, just think a little bit. Yes?
Isn't the carrier already a high frequency component because they don't really assume that it was much greater than the message?
Yes. Yeah, it's high frequency component. Yeah. For this guy only, if we don't consider omega ct for this guy, it is already high frequency, right? So it's like this. So if you remembered, so this is the modulated signal at Fc, right? If we use a low-pass filter, then nothing will be left, right? Yeah, this guy is already high frequency, right? Therefore, it basically means that if we use this guy, multiply the constant, so that part will be gone.
Oh, okay, I misunderstood what you said originally. That's why.
Okay, is that clear now?
Yeah.
Great. Yeah, this is maybe a little bit confusing. So basically, it means that the only thing that will be left is when we have this cosine, multiply this cosine, right? Everything else would be the higher frequency component. So basically, what we left here is as follows. So basically, this RT equals to, this multiply that. So basically, what we're going to have is 2 over pi A plus MT, right? And then we have a cosine omega c of t square, omega ct square, and plus all the higher frequency component. Okay, so if we use a low pass filter, all of this will be gone. Okay, very good. Okay, and how about for this one, right? So now we have a cosine square as usual. So basically what we do is to write that as 1 plus cosine 2 omega ct, entire thing over 2, right? So basically, if we do that, so this 2 will be gone. Well, 1 over pi A plus mt, and 1 plus cosine 2 omega ct. And then we have this here as well. Okay, and clearly, so this item is a higher frequency component as well, right? If after the low pass filter, right? So basically, let's say, I swallow that. I'll take another. Man. Yeah, I think my cough is much better. Just feel uncomfortable a little bit sometimes. All right, let's continue. So after the low pass filter, so basically what we're going to have is as follows, right? It's this one. Right, that's after the LPF, right? The signal will be this one. Okay, so now I give you the entire demodulation graph. So I will draw it here. So basically, our input is our Sm of t, and then, so I'll repeat what we got before. So basically, we have diode here, right? And then this. Okay, and then after that, so we're going to pass the signal through a LPF. Yeah, this is the LPF. And after that, so what we're going to get is, so let me denote. Let me see. So the RT is here. Let's say here is the first signal, and RT is the second one. And the signal here, let's denote that as V of t, right? That's the third one. And the last one, let's denote that as V3 of t. And the last signal here is denoted by V4 of t, right? So that's the number 4, right? And here we can see that this equals to V3 of t, right? So this is the third signal. That's the V3 of t equal to that. Right now we have something like that, right? So basically, that is for this signal, right? That is for this guy already. Right, that's for this guy already. And then basically the last step is nothing but, we call that, so we use the capacitor here. Okay, so the reason we use the capacitor here is to get rid of this DC component. So after that, so our V4 of t would be equals to this guy, Okay, yeah, that is basically how we do that in practice. Okay, yeah, that's the total demodulation process. So any questions? That clear? Yeah, so basically you can check out how the capacitor work in the book. So I think there's a good explanation on this. Okay, great. Okay, yeah, this is the demodulator that I want to cover. And next, let's talk about the bandwidth efficient amplitude modulation. Okay, let's see. Yeah, for the first one, so we're going to talk about SSB. Okay. So now let's just recall a little bit for the disadvantage of the AM or the general DSB modulation. So basically, what we consider here is something like this, right? Yeah. So that's our M of F. So this is our original signal, right? And then, so when we modulate that, so basically, this is what we get. This is F minus F, right? And the magnitude here is halved, right? So this is basically what we got, okay? And so as we said, right? So we introduced the name before. So basically, so we call that USB, right? The upper side load, the upper side band, right? And so we call that LSB, right? So if you assume MT is real, then we know, so this and that are symmetric, right? So this equal to, so this equals to this guy, we take a minus F and then we take a conjugate, right? So basically, they contain exactly the same information. So basically here, so it's kind of waste of the bandwidth, right? So basically, the idea is to transmit only half of it, okay? It could be the lower half, and it could be the upper half, right? For example, let's say, so if we transmit only this part, right? It's called USB modulation. Okay, on the other hand, if we transmit the other half, right, the other half is that, this one, this one. Okay, so this is called LSB. Modulation. Okay, so now let's see how we can do that, right, mathematically. All right. Is that easy to do? Or do you have any idea to how to do that mathematically? So basically, now we only consider half of the signal, right? So we need to somehow cook this thing up, right? Yes?
Can you do a frequency shift and then filter?
Frequency shift and filter.
Yeah, because it's going to be like symmetric.
Mm-hmm.
So if you shift it over,
Uh-huh.
and then you can cut off
It's like,
maybe a half
we,
of it?
yeah, we kind of like passing through a filter to cut this half out,
Maybe,
like this kind of filter, or a band pass filter. Yeah, possibly. But band pass filter, you know, may not be extremely easy to implement. Right? In practice, I think, you know, when we implement band pass filter, maybe it's a like concatenation of low pass and high pass, something like that. Yeah, any other idea? I mean, the idea is not unique, right? This idea definitely works, right? We pass that through a filter, then, yeah, we can have this, right? Is there any other idea? So let's say we don't use that idea yet. Right, let's see, okay, so let's see how we can get this, right? Even if we get this, you know, the task is not trivial still, right? Even if we get this, and then we can move that to here, so that is easy. But how about this part? So this part is the LSB part, right? So basically, we need to kind of cut it in half and shift this part here and shift the other part there, right? It seems pretty hard to do, but let's focus on this first, right? So mathematically, let's see how we can get this, right? So by using all the, you know, mathematical tools that we have learned so far, all the special functions, so is there a way that you can get this mathematically? Right, so what is the relationship between this and the original signal? We'll take half of it, right? Can you imagine if we can multiply this by something to get that?
You multiply it by like the conjugate, because then you would cancel out like the.
Yeah, I think probably eventually that is what we're going to do. But now it's very easy. So let me give you a hint, right? So when we talk about the special function, we talk about the delta function, we talk about the complex exponential function, and we use both of them quite a bit. But there's one function that we didn't use that yet. Do you remember the other function that's left? So what is the integral of direct delta signal? Yeah, unit step signal. So hopefully you still remember it. So let's say if we use that, multiply a unit step signal, UF, right? Remember, the definition of UF is that whatever is bigger than 0, is 1, otherwise it's 0, okay? If you use this, multiply that, can we get it? Yes, right, because basically it's almost trivial, right? So we just use, you know, this part will retain, and this part will be just gone because we multiply 0 with that. Does that make sense? But let's see why we do this kind of simple operation, right? So basically, yeah, the idea is quite simple. Yeah, so basically what we do is as follows. Yeah, let's give a name of it, right? So we call that M plus F, and we call the other part we call the other part m minus f. Okay, so in this case, f plus f will be nothing but mf times uf, right? Okay, and so now in order to use some typical Fourier transform, yeah, we can use that directly, but yeah, we can change it a little bit. So basically, uf equals to half 1 plus a sine signal of f, right? Where this sine SGN, so basically it means that if f is bigger than 0, it's 1. Otherwise, it is minus 1. Okay, so that's this signal, and clearly, so u of f can be written as this, right? So basically, we just shift this by 1 unit, and then we divide it by 2. Okay, so that's basically uf. The reason we're using that is that the Fourier transform of that is easy to write. Okay, and all right, so basically, so this equals to, we use this multiply that, 1 plus sine f. Okay, and that equals to half of this, and this. Okay, so now let's look at this, right? So this part is something that we're familiar with, but this part is not, right? So yeah, let's take a look at, so this is what happened in the frequency domain, right? And so it's kind of clear what is happening, but let's see what has happened in the time domain, right? So this is a multiplication in the frequency, so in time, so that will be a convolution, right? So we know the inverse Fourier transform of f, m of f, that is m of t, right? And what is the inverse Fourier transform of this guy? Yeah, let me tell you. So basically, the inverse Fourier transform of this guy is j over pi t. Okay, so basically, in the frequency domain, it's a multiplication. Then in the time domain, so equals to mt convolutes j over pi t. Okay, yeah, that is basically what is happening. And if we can write that, then we can write down, let me write it down here. So m plus of t, so this is a Fourier transform, inverse Fourier transform of this guy, right? That equals to half m of t plus this guy, right? mt convolutes, maybe you can write j here, 1 over pi t. Okay? Yeah, this is what we got. Okay? And that's it, right? So basically in the time domain, so what we do is that we use our original signal multiply j times mt convolutes with this signal, and then we can get our half of the signal. Okay? And why I want to write it in this way is because, so this is a very famous convolution. So I have a special name for it. So it's called Hilbert transform. Okay, so basically, the definition of the Hilbert transform is exactly this guy, right? So we say, we denote that mh of t, h basically means Hilbert, equals to m of t convolutes 1 over pi t, right? That's called the Hilbert transform. Is that weird? I mean, name-wise, right? So what's called a transform, right? Just a convolution, right? Transform is a Fourier transform, right? Like Laplace transform, that is a kind of transform. So just convolution, why it's called transform? Yeah, I don't know. There's maybe just convention, but it's called Hilbert transform. Okay, it's a very famous transform, and you can see that very often in communication system. Okay, so let's focus on this a little bit. So let's denote h of t equals to 1 over pi t, right? So that's basically, if you consider that as a system, right? So this is basically the unit impulse response of the system. And then we can compute the Fourier transform of it, right? We know the Fourier transform of this guy, right? So that's basically the sign. Right now, the only difference here is that we have a j here. We need to multiply this guy by a j. Multiply the sign by a j, right? So basically, yeah. Yeah, basically, let me see. Yeah, let me see. The Fourier transform of this guy is psi. Right now, I just need to multiply this by j, right? Yeah, I'm getting something that is different from I'm writing here. So who can tell me what the Fourier transform of this guy is? So basically, yeah, let me see. So the inverse Fourier transform of this is that, oh yeah. So basically, if here's 1, then I need to divide j on both sides, right? So then that is, yeah, now it is what I wrote. So it's 1 over j sine of f. So that is minus j sine of f, right? Yeah, so this is what we get. And if we write it down, so write this sign down. So basically, it means that h of f equals to minus j when f is bigger than 0, and it is j when f is less than 0, right? And also, this minus j basically is a phase shift, right? So this equals to e minus j pi over 2, and this equals to e j pi over 2, right? So if we write down if we sketch it, right, of this guy, we can see that, so the magnitude of h of f. So now when we sketch it, so because it's complex, so we cannot just draw everything in one figure, right? So we need to distinguish between the magnitude and the phase, right? So magnitude here is 1, and the phase. So basically, it's that when f is bigger than 0, it is minus pi over 2. It's like this. And when f is less than 0, that's plus pi over 2. Okay, so that's the phase. Okay, so basically, what does this transform do is that, remember, so in the frequency domain, it's a multiplication, right? So it basically means that on the positive side, so we shift the phase by minus pi over 2. So on the negative side, we shift the phase by pi over 2, right? So this is what Hilbert transform is doing exactly. And of course, this is ideal, right? So in practice, this may not be implementable, but mathematically, so this is what we want. All right. Okay, so maybe I'll continue on this in the next lecture. So next one, so in the next lecture, so we're going to write down so this signal, so using what we have covered so far, using the Hilbert transform, okay, and see how we can. So this is basically the signal generation, and then we can see how we're going to demodulate it, okay? Thank you.